Hello everyone, welcome back to my YouTube channel, and today I'm going to do something a little bit different. This is not going to be part of my main series on Satisfactory, but rather I'm going to show a tutorial from my electrical engineering perspective on fluids. So I do plan on increasing my power production, but to do that, I'm going to need some good design. I'm kind of maxed out right now at this power plant and the one over by the coal generation that I have. So I did some thinking on this, and I just think it's good to have multiple perspectives on this kind of thing. I know there's a ton of tutorials on this, but here's something that you could try that's not going to be too difficult to set up. And you don't have to do this with just one industrial buffer either. So right now I have a oil extractor set to 600 meters cubed per minute on a pure node. It is bringing oil to some of my system down that way, but I split this off here and I'm bringing it up to this buffer. The reason I have this up here, it kind of builds off the water tower idea. But on the output, I'm only going to use the Mark 1 pipes because I don't want to exceed 300 meters cubed per minute, because I'm going to show kind of what one can do. Let me just put this valve back because I need it for what I'm going to explain. So on my output, I want to set this to, oh wait, oh sorry, I don't need the top valve because it's going to be maximum of 300 meters cubed per minute. Sorry, I'm having a hard time speaking. But anyway, so the general idea of a fluid system is you don't use more than what you have, and that's pretty much there is pretty much the same concept with electronics. Like let's say a system is capable of producing 10 amps, but your downstream components require 15. You would be overloading it and it wouldn't power, and there might even be like damage or something. It depends on the application, but anyway, so to simulate the idea of having a load, I'm going to be using smaller buffers here. Get this out of the way. The important thing to note is you do not want to exceed your system's capability. To do that, you gotta keep in mind that you cannot use more than 300 meters cubed per minute. So, I want to set each of these to 50. So then these outputs, let's say if they were like refineries or whatever, each one of these would consume 50, meaning that the total amount would be 150, but that means that we have 150 excess fluid, and sometimes it can cause overflow or like clogs in your system. So what do you do with the excess fluid? Many other tutorials say that you want an overflow pipe, but the thing is, I don't think it would be a good idea to completely load the system up to 300 meters cubed per minute, because if let's say that the input here never reached that flow rate, let's say that the input flow rate was less than, the industrial fluid buffer would then empty, and then the downstream system would then fail. So you just got to make sure that your input flow rate is going to be higher than your output flow rate, so that your buffer never empties, or at least it won't empty to the point where it'll be out. That's the important part. So yeah, so on the output here, I've got what is known as a reverse U-bend set with an output limiter of 100. So that means that I have a total of 150 plus 100 is going to be 250. 250 total out of 300 possible, which is fine. And then so this will basically allow that these pipes will fill first, and then this will come to the overflow into the buffer that we want. So if I hook this up, it'll actually fill up rather quickly because it's pretty much optimal right now. So let's just test it. So we should be seeing, oops, I set up a little hypertube here. We should be seeing these fill up rather quickly. Yep, see? So that this pipe is filled, this pipe will fill soon. So will this, and now we've got consistent flow. So these are peaking out pretty much at their maximum flow rate. That means that these will fill up relatively quickly, not super fast, but and then the excess is going to be set to the 100 and the 100, and then as this fills, this means that the overflow will fill faster than the other buffers here, and then you pretty much see that there really isn't going to be negative net. For the most part, it will be positive. There is a little bit of sloshing because it's trying to go between this buffer and this pipe. So it's just important to know that your output needs to be full so that everything is working at 100% efficiency, pretty much. Yeah, these will just fill up pretty quick, minus the sloshing. It will probably take around, I don't know, like a couple minutes to fill these. So I'll just let this kind of even out here. And then, oops, I did it again. Once I let them fill, I'm going to show you what happens if, let's say that you have an over demand in your system. But I'm gonna let these fill up a little bit here. But yeah. Yeah, so the net speed should be around 250 minus some fluctuations in the pipe system, because it's not, the flow rate's not going to be ideal regardless of what system you have set up here. And then this buffer should also be filling and draining at the same time, so that this will never really come down, which is important in the system. So let's just wait for these to fill up. I mean, I don't have to wait for the whole thing, but this is pretty much almost full because the flow rate is much faster on the overflow output. So that's full. And typically that would mean that the rest of the pipe system will fill up a little bit faster too, so. Oh, and another thing to kind of realize is that once the buffer gets to the like the maximum, like if the buffer reaches 300 meters cubed, the pipe will have less chance for sloshing around, because basically it's meeting the level that the fluid is on your output. So that means that the net will be mostly positive. It's not 100%, again, it's not 100% perfect, but yeah, so yeah, these will just kind of fill up relatively slowly until they're completely full. But now what I'm going to do is go back up. I'm going to disconnect my system because I do not want my entire downstream thing to empty. So deconstruct this. I'm going to say full pipe network flush. So now all of those are empty. Let's say that the I don't think the overflow buffer would be a bad example, but let's say that we wanted to have, let's say that we didn't know about the whole process here, and then we put a pipe, a Mark II pipe that can handle 600 meters cubed, and then we set, well, let's say that the output of the system on this side was, I don't know, let's say 600 and 600. Oh, that still wouldn't work. It'd have to be both 600. No, I think but yeah, let's say that one of these were to be completely open. So that means we're asking for 50, 100, 700, and 800 meters cubed. That means that the output buffer, I mean the this input buffer, this is gonna empty rather quickly. So I'll just show you that. Oh shoot, downstream pipes. Bottlenecks. Right. Okay. So let's see what happens here. See, so our drain rate is now over 600 because that's what our system is asking for. Yeah, I don't see any potential mismatch pipe here. I mean, granted that the input may be able to match the input may be able to match that expected output, but this will start to drain because I've got other systems that are asking for oil. That means that this will just decrease too, and then this has to work even harder to pump fluid up. But to make this drain even faster, we're gonna really overload the system. So I'm gonna say I'm gonna increase this to, oh, it's already full. That's why it's, because it's no longer flowing. Shoot, I didn't think of that. Do I have enough for another big buffer? Yeah, I do. So let's say we increase the buffer size. Which asks for a lot more fluid. That means that this will fill up really, like, try to fill up really fast. And let's even overload this to, I don't know, like 80. So yeah, now the system's going to start to struggle, because effectively we're asking for, what's the total going to be? This is set to 600. 600 plus 80 is 680. 680 plus 50 plus, let's just make this 50, I guess. So 600 plus 50, 100. Anyway, it's going to be over the 600 meters cubed per minute by quite a bit, and that means that this will start draining quite quickly. We are at a net maximum of about 100 or so, depending on the downstream effect. Oh wow, it even ramps up to like 300 at some points. And not only that, our valves will not even work 100% efficiently, because pipes are emptying faster than what, because these need 100% to work right. So this is not full, not full, not full. This is filling at a very fast rate. But now, and I'm sorry, I'm just kind of repeating the point. This is going to be draining faster than it can fill up, because it's asking for much more than it can actually handle. Downstream, the net is a lot more. So as this keeps on decreasing, and yes, it will fluctuate. So there is that. But I can make the demand even higher if I really wanted to. Yeah, there's going to be quite a bit of sloshing because of the way that I have it set up now. So yeah, this is a less than efficient way to set up the system, that's for sure. So yeah, you just gotta be mindful of your total consumption on your line. Basically, you're limited to the maximum flow rate of the pipe. Sorry. I'm misspeaking a little bit. If it's one system, it's going to be limited to the maximum flow rate of the pipe. But if you have parallel systems, it does increase. Net increase, anyway. Because, so let's say if you had a second buffer up here, it would make up the difference between the two pipes, and then you would have a way to actually meet that demand, because basically you would be adding another 600 meter cube per minute pipe into the mix. So yeah, thanks for watching. I'm sorry if I rambled a little bit and repeated my points, but yeah, this is gonna sometimes fill and sometimes drain really, really fast, so it just kind of is limited based off the input flow rate here. So thanks for watching.